Yet another important video from Ushendra's engineering tutorials. It's a damped cosine function and its Laplace transform. So what is a damped cosine function? It's a continuation to yesterday's video. It was sine in the previous video and it's a cosine function over here. The proof is very much similar to that, so let's finish in within few steps. So the given function x of t will be e raised to minus at cos omega t u of t, and the Laplace transform of x of t results in capital X of s. It's a notation in Laplace transform or S domain, which will be equal to the function e raised to minus at cos omega t multiplied with e raised to minus st integrated with respect to t from 0 to infinity. Going ahead, x of s will be equal to make the simplification, to make the analysis easier, cos omega t is replaced with its Euler's identity, such as e raised to minus at, which is next to cos omega t, is as it is. Cos omega t in this expression is substituted with its Euler's identity, e raised to j omega t plus e raised to minus j omega t upon 2, multiplied, the whole equation is multiplied with e raised to minus st and integrated with respect to t from 0 to infinity. This is what. Going ahead, further simplifying this one, these three terms should be multiplied. Okay, the further simplification will be multiplying these three terms and taking out exponential as common, even negative as common in the power, and t as common, t also as common in the power. What we have is exponential as it is. This is the term exponential. Negative is taken out as common, so s plus a minus j omega t would be the resultant when multiplying all these. And the second simplification in this expression is, now these three terms will be multiplied and the resultant will be exponential raised to negative as common, so all the three terms has negative that came out, so we'll be left with s plus a plus j omega and t also as common from all the three terms. Okay, so this is a simplification, and this equation, these terms are integrated with respect to t from 0 to infinity, being the lower and upper limits respectively. Half comes out because we got to do nothing with the half in the integration, and which is equal to x of s. Integrating the above equation with respect to t, and guys, recollecting the previous equation once again, x of s is equal to 1 upon 2 integral 0 to infinity e raised to minus of negative came out as a common, s plus a minus j omega into t plus e raised to minus of negative came out as common, s plus a plus j omega into t, and the integration with respect to t. So the first term, once again, it's similar to e raised to ax dx. Now in this case, this equation is integrated with respect to t, so this will be the constant. So integrating this one, this will be appearing as it is in the numerator, and in the denominator will be having this constant term like this one, because integration is with respect to t. And coming back to the second term, it's as it is, e raised to minus of s plus a plus j omega into t, and in the denominator we'll be having this term, because this is the constant in this case, so that comes down in the denominator as it is. So this positive, it's as it is, and we are done with the integration. So limits of integration, the upper limit is infinity and the lower limit is 0, and half comes out, which is equal to x of s. Right, so plugging in this expression, in the above expression, plugging in the upper limit and lower limit in place of this and in place of this. In the denominator we don't have anything, and simplifying this one, what happens is plugging in the upper value in the infinity in the first term, right, e raised to minus of entire term as it is, entire term, and in place of t we have infinity, which is the upper limit, minus entire term into 0, which is the lower limit. This is for the first term over this one. This is for this one, and the denominator has got no change. It appears as it is in the further simplification. And the second expression, plugging in the same upper limit and lower limit, in this case it continues e raised to minus of s plus a plus j omega into infinity, which is the upper limit, minus e raised to the entire term into 0, which is the lower limit. This is the plugging in values of the upper limit and lower limit in the numerator, and the denominator we have as it is, and this positive also as it is, which is equal to, we cannot cancel half, it appears, which is equal to x of s. Okay, so there is a small further simplification. This term, this we got to know something. The first term, this one, this will be minus infinity, because the entire term is multiplied with infinity and we have a negative, and this one becomes 0 because the entire term is multiplied with 0, and this becomes minus infinity and this becomes 0. Exponential rise to negative infinity becomes 0, and e raised to 0 will be 1, and these are the transitions. We don't have, there are some simplifications like e raised to 0 will be 1, we had e raised to 0 over here, so that will be 1, and we had a 0 e raised to 0 over there, and so even this becomes 1, and e raised to minus infinity, that will be 0, and we had another e raised to minus infinity over here, even that will be 0. This is the simplification, and the denominators are to be multiplied now. Further simplification, x of s is equal to half into half doesn't cancel yet. The entire equation, the denominators are multiplied like this one, s plus a. This is taken out as common, s plus a over here, s plus a over here, s plus a over here. The real terms are taken as 1 minus imaginary minus j omega. Right, you can clearly see this is like a minus b into a plus b. S plus a is considered entirely as a and j omega as b. S plus a, this will be a minus b into a plus b, like that one. And cross multiplying, what we have is this term comes over here like s plus a plus j omega, and this term comes over here s plus a minus j omega, and in the numerator you can clearly see that something gets cancelled, s plus a as it is, but look at the imaginary term, it's plus j omega and this is minus j omega, so those two terms gets cancelled. We don't have that anymore. And s plus a, that will be 2 times s plus a, and this would result in a minus b into a plus b, such as s plus a whole square minus j omega whole square. Why? Because a minus b into a plus b results to a square minus b square. In the same way, s plus a whole square minus j omega whole square. Simplifying the above equation, what we have is x of s is equal to, we have half as it is, the denominator will be s plus a whole square minus j omega whole square, and in the numerator we have 2 times of s plus a, and here in the denominator, in the expression denominator, we have minus j omega square minus, no, j omega square, and this square is applicable to j also, and so that would result in minus 1, and the entire term will be minus omega square, and we have a negative over here previously, and this negative gets cancelled, negative into negative, that becomes positive, and this is the resultant existing equation. And something else here to be cancelled, yeah, we have 2 in the numerator and 2 in the denominator, that also gets cancelled like this one. This is my final expression, Laplace transform of here e raised to minus 80 cos omega t u of t results in s plus a upon s plus a whole square plus omega square. Another important point to be remembered is inverse Laplace transform of s plus a upon s plus a whole square plus omega square results to e raised to minus 80 cos omega t u of t. These both equations are known as Laplace transform pairs, and very important in Laplace transform analysis. Okay, this is all for today's video. Thank you so much. Stay home, stay safe. If you find this video useful, please subscribe my channel Ushendra's Engineering Tutorial. Thank you so much.